Thank you, Seema. So the first speaker of the session is Alorika. She will be talking about reconstructing and distinguishing the formation of and evolution of supermassive black holes using multi-wavelength gravitational wave observations.
Okay, thank you, Kanak. So let me start. So today I'll be talking about this work that we did in collaboration with Shobik, Enrico, and Ajit. So this is titled as the Reconstructing and Distinguishing the Formation and Evolution of Supermassive Black Holes using Multi-Wavelength Gravitational Wave Observations. So let's start. So we know that there are various classes of astrophysical black holes which we can distinguish according to their mass ranges. So there are stellar mass black holes which are usually formed from the collapse of massive stars and which we have observational signatures from electromagnetic and as well as gravitational wave detectors that are currently observing like LIGO, Virgo, Kagra. So we can observe the stellar mass black holes, and there is an elusive intermediate mass black hole range which we do not have enough observations yet, but these are like kind of under theoretical predictions that they might be present, and we have a few events which fall under lower end of this intermediate mass range. So we think that when this future detectors will come up, we will be able to detect more of this intermediate mass range black holes. And then there is the supermassive black holes, which are now observed in almost at the centers of all the galaxies that we are observing. And also as we see earlier in time at very high redshift, we are observing the supermassive black holes at the center of all galaxies. Either through electromagnetic observations, but GW observation is still not available because we don't have the required detector to detect those. So now if we have this whole mass spectrum of black holes, and we know the origin of only one of this. So my topic will be to talk about how this supermassive black holes are formed, which have a very high mass range, above 10 to the power 6 to 10 to the power 9 solar masses, and how they grow to this such high masses. Now, there are various mechanisms which have been proposed to tell that okay, how this huge mass growth might have happened starting from the early universe. So what is thought that in the early universe at a very high redshift, you had some black hole seeds which are like smaller mass black holes or intermediate mass black holes, which were formed through some phenomena, and they eventually accreted mass and merged with other surrounding black holes of similar or near similar masses, and eventually grew to this huge mass range. Now you might ask, can we not have the same phenomena as like stellar mass black holes, like we form a supermassive star and that collapses to a supermassive black hole? So the answer is no. We cannot form such huge stars because the formation of stars from a molecular cloud is formed through some fragmentation and all. So there you cannot keep star to be formed to that high mass to give that will give birth to a supermassive black hole directly, like we can see in stellar mass black holes. So that scenario is kind of ruled out, but still there are some ways in which we can reach up to some higher masses, but those ideas are also under debate. So the most dominant idea currently is this from mass growth through accretion and mergers from early universe to the day we are having these current observations using JWST and all. So here in the right hand side, you can see a plot which tells that how this mass growth might have happened. So in the x-axis is mass, and in the y-axis are redshift. So at high redshift, that means in long back in time, you might have formed some black holes, which are like, let's say at around between 18 to 20 redshift, you form some small, lower mass black holes through some way, and that eventually merged with other black holes. So this whenever you have two these dots, which means that they merged with the other black hole, and then these lines are the accretion, they are undergoing some accretion. So these are various ways in which it can go to such high masses. So it evolves along these pathways and reach the high mass at low redshift, where we are currently having EM probes. And so there are multiple ways. We don't know what is the exact way. So this is yellow is one of the proposed models, and then this green where you have less number of mergers, then you have this red where you have a little bit more number of mergers. And then one more thing is that this blue line, you can see it starts at a higher mass, so you can have a higher mass seed to start with, and then you can eventually go to the SMBH mass range. And on the background, you can see this waterfall-like plot, which is the LISA horizon. So LISA is an upcoming GW detector, space-based detector, that will be able to observe this full evolution of these black holes from early, very high redshift to the current low redshift and today. So you will be able to map out this full mass redshift plane for this black hole growth. So there are various models which people have proposed that they can grow through multiple such ways. So one of this is called a light seed model. So here what you have is the seed black holes that I talked about are formed at very high redshift and have a relatively lower mass from about 100 to 10 to the power 3 or 4 solar masses. So they are formed at redshift of 15 to 20, and then they eventually accreted and merged with other black holes to give rise to the supermassive black holes. So there are various other variations in this light seed scenario itself. So these are all simulations where people simulate the dark matter halos and then simulate the galaxies and then the star formation in them. Then they have black holes in them and then how they grow. And then you have this how these black holes evolve, how they merge with each other, and all this simulation people have done. And those simulations, as you change some inputs and like various how the accretion happened, what was the distribution, initial mass function of the seeds that you put, how they merge, what was the dynamical friction, what force did they at all merge, or did they stop at some distances, and all those inputs are there. So that gives rise to variety of models. So these two that you can see here on the left hand side are light seed models because they start at a lower mass at very high redshift. And then there is this heavy seed model where you start with a relatively high mass. So you can see that it starts above 10 to the power 3 and it eventually grows to the SMBH mass range. Then there are people are also telling that it might be a combination of these seed models, light and heavy seed in some proportion. That also we don't know, because the heavy seed model is very highly constrained. The formation of a heavy seed, like a 10 to the power 4 solar mass black hole formation, is very constrained. You need very favorable conditions to form such high mass black hole. But the current observations say that we have SMBHs in almost all galaxies. So you have to match the abundance of the seeds with the abundance of the SMBHs that you are observing. So there are a lot of debate that which is the correct model, but yeah, these are the most probable possibilities that you can have regarding the models. Now, what we will do with the future GW detectors? So in 2030s or 2035, we will have the LISA, which is a space-based detector that will observe in this frequency range of 10 to the power minus 4 to 0.1, which is like very massive, the high mass end of the from intermediate to high mass end of the black hole spectrum. So once this detector is up, you will be able to detect all the black holes in that mass range. And then you will have the decihertz detector like LGWA, which is a lunar detector, and it will observe in a little bit higher frequency range, that is a little bit lower mass range. And then we have the third generation ground-based detectors like Cosmic Explorer and Einstein Telescope, which will observe further higher frequencies and lower masses. So combining all the information from all these future detectors, we will be able to understand this supermassive black hole mass evolution. So let's see how we can do that. So now, since the detectors are not up yet, we have to simulate the future observations. So what we do for that is if we have the data from where people simulate this SMBH formation, the models that I talked about, people have done those simulations. We have those data, and we simulate the detector. Like we think that our detector will be like this, and we think that our detector will detect this much amount of mass and redshift range and all that also we have simulations. We combine those two and we calculate that, okay, how many detections we will have from all those detectors. And once we have the detections, we know that we won't be able to uh, exactly pinpoint the true values. We will have an error bar, that is this Fisher matrix information that we call. We'll have posteriors on the binary parameters, and using those posteriors and the selection function of the detector, that is your some detectors in some region are more prone to detect some events and other than some other region. So for example, in this plot, these are the selection function plot. So what this tells you is that at low redshift and at lower redshift, you are more prone to detect more events, but at higher redshift, you are less prone. But when you are trying to infer the true distribution, you have to take into account your detector's bias, that your detector has a selection bias. It detects nearby events more than further events. So that is called the selection function. So once you simulate your future observations and you take into account your detector properties, you are good to go for to reconstruct the underlying distribution. So what we did here is we took all of these various models and tried to simulate the future observations, where you can have, let's say, only light seed model, or you can have a heavy seed model only, and you can have a combination of light seed and heavy seed. And in the heavy seed model is that the since it starts at a higher mass, the 3G detector is not at all applicable because there are no events in this range. And in the light seed model, you can see that there is not a single detector which is contributing to the whole detection. All three of them are contributing, and you are getting detections from the full distribution if you use all three of them. If you use just a single of them or two of them, you are not able to get the information from the full distribution. So you need a full network of detectors to get the full information from your underlying distribution. So now, once we have that simulated data and the selection function, our goal is to go back to the true distribution. And the speed det is the detected data that you will get from detectors. So once your detectors are up, you will get the detected data. The selection function is calculated. You know the detector features that you already have the information. The only information you don't have is this true distribution. So once you have the detected data and selection function, you will use this to go back to the true underlying distribution, which we started with. And so this is one of the examples that how close can we go to the underlying distribution. So here you can see the three detectors that we use, the LISA, LGWA, and 3G. The black the line distribution you can see is the true distribution that we had assumed that, okay, let's take a light seed model and start and go back to the light seed model. How close can we go? So that is this true data, the true underlying astrophysical model. And the gray
Sorry.
shaded region is the
Alorika, you
reconstruction.
just have 1 minute left. Sorry.
Okay, fine. Yeah, so this is the gray is the underlying reconstruction that we could do. And and here you can see that how the multi-wavelength approach is getting used. So if you use just LISA, you won't be able to reconstruct this part. If you use only LGWA, you won't be able to reconstruct this part and the high mass end. And if you use only 3G, you won't be able to get the intermediate to high mass end. So you need a combined network to get the full reconstruction. So that's what the multi-wavelength observations are in use. And this is the combined reconstruction with the marginalized distribution. So you can see that there is an error bar, and we can pretty well reconstruct the underlying distribution with a little bit error bar, because here you have very less number of events, so the uncertainty is a bit more. And this goes well for all the models, and this is for a heavy seed model where you don't have events from the 3G detector. Here only LISA and LGWA are enough. But yeah, so and in the heavy seat model, one of the important things is LISA will be enough. You don't need to have a network because it is already in the high mass regime, and LISA is very well suited to detect that high mass regime. So their multi-wavelength approach is not that much required. And now the last part is once you have these reconstructions, how well can you distinguish between those different models? That, okay, if I have the reconstruction, whether it has come from a light seed or a heavy seed. So let's say I have this multiple light seed models where you can have similar light seed models also, as you can see in this plot. Two light seed models are very much similar. And here you have heavy seed and two different light seed models. So for that, we use the scale divergence, where we check that how much similar are two models, and by calculating this DKL. So if you have two distributions, how close are they? And a lower DKL value will tell you that they are very similar. And if you have a higher DKL value, they are much different. And this is the final plot. And so here what I have plotted is you have multiple light seed models, that is a true data, and you have done reconstruction using this detector data for all those models. So when you see the diagonal elements, that then you are getting the DKL between that model and the data reconstruction itself. So you see a lower DKL value. That means your reconstruction matches best with when you are matching it with the true data itself. But when you match it with other models, you see that higher DKL values, which means it is not matching with the underlying distribution. So you can say that, okay, if I have the reconstruction, I can say which is the light seed model and whether it has come from light seed or a heavy seed. So yeah, and these are the important equations. So you have various models which predict the formation and evolution of the supermassive black holes. This future multi-wavelength DW detections would enable us to detect mergers across this a wide range of masses and redshift. And you have the detected data along with your proper selection function will enable you to map out the underlying mass redshift distribution of the black holes, and you will be able to distinguish between various models. But there are a few difficulties. If you ask, I'll tell you later. So yeah, thank you.